Right. So let's look at this monitor really quick, just in case you forgot what we did last week. Okay. So it's a combinational logic design, and every single light will be shorted to a wire. So G1, Y1, R1, G2, Y2, R2. These are just the wires, right? And everyone represents a LED, one of the 6 LEDs. Okay. So eventually we need to figure out the inputs to output a certain pattern for each entry, each row here, to show that signal light that is needed during that period of time. Okay. So the inputs could be anything. It's a decoder, so the inputs could be anything. However, if you count the number of entries we have, eventually we got 6. Okay. So for 6 entries, if you have 2 inputs, then the maximum number of entries you can have will be 4, right? So it's better to have 3 inputs, can give you up to 8 different combinations. But we just don't have to use the last 2, right? So in that case, A, B, and C are inputs, and all the columns on the left-hand side are outputs. Okay, so these will be signal lines in your Verilog. Do I have an example here? Yeah, like this, okay? Light 1 and light 2, okay? So light 1, for example, is G2, G2, Y2, R2, and light 2 will be G1, Y1, R1. Okay, everyone has 3 lights. And they're register type, data types, okay? And from this truth table, you can derive the logic expression for all these columns, every single column. It's a decoder design. And how do we do that? Just refer to last week's notes. I think you can find out. I think at least I did maybe 4 or 5 of them for the first example. Okay. So looking at the inputs, it could be, for example, for the first one, R1, right? R1, it is A naught, B naught, C naught. Is that correct? Okay, so for R1, it is A naught, B naught, C naught, or A naught, B naught, C, or A naught, B, C naught, or A, B, C naught. So these are all the SOPs for R1. So similarly, you can find out the SOPs for all the signal lines, and it simplifies that a little bit. So eventually you are getting all the signal lines. And these are just assigning, right? So assigning that logic expression over here. But in the behavioral modeling method, you don't need assign because it's using this blocking. It's using a blocking assignment. You directly write down the logic expression that are derived from the truth table. Any question on this?
So basically writing the decoder?
Yeah, if light 2 is, for example, G2, right? So it's going to be the logic expression for G2. And how to start this code is already provided over here. And this is example for the second task, for the rush hour 1, right? But for the first one, because this is already provided, you can modify and make the first one work as well. I think this is the first one's example or not? No, this is a decoder case 1. This is the one for... Oh, this is another example, trying to let you practice with the LEDs first. So you don't have to do this one, okay? Just a testing code. Okay, this is a real code for the task 2. Just giving you some examples to begin with, right? So you can directly use these ones and fill in the blank areas with your logic expressions and figure out all these conditions. So what are the conditions? Let's think about it. So whenever it reaches a count max, because every time when it changes the state of the lights, you need a time delay. So time delay, you need a counter max. You know, the counter is counting towards count max. So what's the other condition here, which is needed? If you look at the truth table, are able to tell? So whenever it reaches count max, you switch to the next state, okay, of the pattern. So it keeps moving to the next one, next one, next one. Whenever it reaches a certain state, you're gonna come back. The thing is, this counter is not counting to 8, right? You only have 6 states. However, 3 binary inputs will give you 8 states. If you're just simply adding a 1 to it, there will be 2 inputs without any outputs. So for example, after 110, what's the next input? 111, right? Because it's adding 1 to it. It's not like a CPU, which is pretty intelligent. This one doesn't know it. It's a very simple adder. So it's adding 1 to this input. You want to avoid that. So eventually, whenever it reaches 110, right, you want to reset it. So that's why you need an AND logic. Okay, if it equals counter max and it reaches, reset it. If not reaching it, don't reset it. Keep counting, right? So that's the logic of it. The first one is even easier. The first one is just cycling through all the 6 states, and the second one requires a rush hour input. So it's a register being used over here whenever the switch is turned on. That signal is being passed to this register type, and eventually you are using this one as a case, right? So during the rush hour, you turn on the switch, and it's gonna do this part of the code. And if it's a 0, so the rush hour, it's not during the rush hour, so the switch is off, and you need another part of the code, very similar to the first one. But the only difference is the condition, because if you use the rush hour one, you're having one more entry, so the input becomes different. Because the first one is counting to 101, and the second one counts to 110. So the condition has to be changed. In that case, you need a different block of code, very similar to this one, and have to modify the conditions over there. Really simple lab, I think. Just trying to wrap up what we have learned for combinational logic modeling. Really don't have any new things. Okay, practice on how to design a decoder to implement a real-world application, and convert to decoder design and implement it on the FPGA board. That's it. Is that clear?
Yeah.
Any questions? Not for now. Okay, you can start working on it. Hopefully, people can finish it early today, so we can, enjoy the evening. Can go home.